So hello and welcome everyone to our today's webinar, Simplify Diagnostic Applications Using Service-Oriented APIs. So what can you expect from this webinar today? In a few minutes, we'll be talking about the difference between the classic diagnostic approach and the service-oriented diagnostic approach, where this need for the service orientation comes from, and how you could benefit from implementing a service-oriented diagnostic approach throughout the entire life cycle. But first, give us the chance to introduce ourselves. We are two today hosting this webinar. On my left-hand side, Andreas, would you like to start with the introduction?
Sure, June. My name is Andreas Fach. I'm a team lead here at Softing Automotive Electronics. In my team, we are responsible for the smart diagnostic engine that is previously the MVCI Server, the D-PDU API, and now also the smart diagnostic API, to which we will come later.
Okay, thank you, Andreas. So my name is Julian Meyer. I had different roles here at Softing. Today I'm here as a project manager, mainly for external projects. So if you have a project together with Softing, there might be the chance that we could work together. And my main expertise regarding diagnostics comes, I would say, from the after-sales area. That's where I have the most know-how. Okay, thank you very much. Let's get started. I will just quickly go through the agenda. So in the beginning, we will be talking, as I mentioned before, about the classic diagnostic approach we are having today. But of course, we have new requirements coming from main drivers like automated driving. How could a solution look like to these new requirements? Andreas later on will present you some detailed examples for the service-oriented approach. And in the end, we will give you a summary. Just one short note, you will mention in the top bar of the Teams display, there's a section called Chat and FAQ. So whenever something comes to your mind, please do not hesitate to just type it in there. We will later on in the end of this presentation go through the questions and answer them together. Yeah. All right, let's get started. So as you can see here, highlighted in high blue, this is the classic diagnostic approach, and everything you see here is highly standardized and in use for many years. Starting from the bottom, you see the D-PDU API, which is the abstraction layer to the hardware interfaces you see on the bottom, which realize the connection to the vehicle. And the D-PDU API takes care about the communication to the vehicle, communication protocols like timings, and handing over the diagnostic services from the layer above. The layer above is the communication engine here, MVCI Server or D-Server. This is mainly responsible for the interpretation of these services based or driven by the ODX data you see here on the left. So this is the description file for these communication services. And even one layer above, you see the sequence engine here, OTX runtime. And OTX is mainly being used when you have more complex or complicated use cases where you need to consider and merge different information. Flashing, for example, could be used by OTX, a flash script, or test automation is also a high-level use case where OTX could be used. As I mentioned, all this information or all this highlighted in light blue here is highly standardized and in use for many years. And this part we will later on reuse. So please try to keep in mind that everything what you will hear in the following is always based on these highly standardized layers you see here. Just to finalize, the application you see on top in dark blue, this is kind of use case specific. You have the great variety between engineering, production, and service. And for each part of the life cycle, you have different use cases, and therefore you will be needing different kinds of application with more or less detailed information. An engineer, for instance, would need an application where he can really choose what kind of services he would like to send to a single ECU. This is the diagnostic approach of today. What comes next? We have, as I mentioned in the beginning, megatrends. One important megatrend, of course, is the autonomous driving. And with this, you could imagine that there's a lot of distributed functionality within the vehicle. For instance, you need the steering functionality, you need the braking functionality, you need functionality from the powertrain. Also some sensors to detect people on the street, for instance. And this functionality requires a lot of computing power within the vehicle. And this then in the end leads to this high performance computer architecture you see here, based on a, I would say, zonal architecture, and then putting the high performance computers on top. So you have a real-time information within the vehicle. And of course, the cloud access is very important as well, because you would like to update your vehicle over the lifetime. You would push some information into the backend for further analysis. What does now that mean for diagnostics? Again, we have the cloud and remote diagnostics here, as I mentioned before. You now see here on the right upper corner the tester. So with cloud and remote diagnostics, you have the ability to directly have a one-to-one connection between a tester and the vehicle, no matter where the vehicle is on the planet, and diagnose it directly. The cloud access is then pushing data into the cloud, for instance, for the vehicle health. So what kind of status does the specific vehicle has at the moment? And this information is then stored in the cloud. And we have the autarkic diagnostics. Again, one example would be the vehicle health, which could be performed on the vehicle. So in that world, the vehicle would send in information about the status constantly to the backend, and the diagnostic running autarkic on the vehicle gathers all this information. What do these requirements then again mean for diagnostics? As I mentioned, we have on the top the tools, as you know it today, engineering tools or after-sales tools, which use the diagnostic stack of today as the connection and diagnosing to the vehicle. But of course, these requirements, which I mentioned, also make it necessary to put more diagnostics on the vehicle. So not only to diagnose single ECUs, but also entire vehicles, which you see here on the left-hand side in vehicle, and the cloud use case as well for, again, vehicle health, campaign management, and use cases like that. The most important part about that is that you could implement this diagnostic stack completely and reuse it completely through your entire life cycle, from the engineering to the after-sales tool. And these diagnostic functions, which are used with the diagnostic stack, the requests, are just implemented once in the beginning, then tested, and then put into the field and always reused. This is the main advantage of this approach. Okay, so far about the advertisement block. Would like to hand over to Andreas, who gives you more details about the solution.
Okay, I would go into a bit more details. What do these requirements mean for our diagnostic stack? So let's summarize quickly. We want our diagnostic functions to be developed just once, and best in engineering, released in engineering, and then reused in production and after sales. We need our diagnostic functions to run on different environments. Classic would be inside of the application, directly connected to the vehicle. But now we also need it, for instance, running on a VCI that is connected to the vehicle. or directly inside of the vehicle. These diagnostic functions, we need to trigger remotely, especially if they're on the VCI or inside of the car. So we trigger them from a PC application in case we have an interactive tester where a user sits in front of the tester and we have a back and forth. We also trigger this in cases where we have automation. In other use cases, we need to trigger it from the cloud. For instance, campaign management, fleet management. If you want to update your fleet to a specific software version, specific ECUs, you need to be able to trigger it from the cloud inside of the vehicle. And thirdly, we also have the autarkic use case. In this use case, the vehicle itself can, for instance, decide when it's in a safe state, create a vehicle health report, and upload it itself to the backend without being triggered externally. So let's see the pros and cons of today's approach. Today we have a diagnostic server. It has an OTX runtime on the top, which is fed by OTX data. And beneath it, we have an MVCI server who is also being fed via ODX data. The advantages of this system is that we have, for MVCI, we have a standardized API data and standardized API. We have in-depth diagnostics, and it's a very mature system. For OTX, we have the possibility to easily go cross-ECU diagnostics, and we also use standardized data. What are the cons? Well, for OTX, you do not have a standardized API, and also the access is data dependent. This means you need to know the OTX script names, you need to know namings of variables, all the kinds of things that change between cars and versions and that you put inside of your application, making your application very dependent on these namings. For MVCI, well, the cons are, it is very hard to learn. We have 1,500 functions. We see it's many OEMs struggling with it to get efficient programming done. You again have data-dependent access. This means inside your code, you need to know what is the service name, what is the parameter name. You need to be an ODX expert, an MCD expert, to be able to even write a simple application. And also, it is not remote capable. So to address these issues and also to handle the new requirements, we use our smart diagnostic engine. At the bottom, you can see that everything we previously created, we reuse. We have our standardized D-PDU API, our MVCI server, and our OTX runtime. The Smart API extends this by offering a simplified and a reusable, remote-capable API. It abstracts from using ODX diagnostic services to diagnostic functions. But what does that mean? I'll give you an example. It means, for instance, when wanting to read a measured value, the programmer no longer needs to know the diagnostic namings, service name and format, which differ for each ECU and each value he wants to read. He can simply ask the SDA for the available measured values, always using the same method. It is not data dependent, and schedule then how often he wants to receive an update. He no longer needs to be an ODX or MCD specialist to do this. This way, the SDA makes it not only much easier to use, but greatly increases development speed of applications, often making previously expensive projects development quicker and feasible. Additionally, any program developed on the SDA is immediately remote capable. So, also, to meet some of the other requirements, the SDA is available on Windows, Linux, iOS, and Android. And as you saw previously, we have our standard devices in the middle. For maybe a lot of people know the Winnie 2000. And as a teaser, we have the newest device out there coming 2025. It's a very high performance device capable of gigabit flashing and running, for instance, Linux container so that you can develop your own software on it. But how does the SDA achieve this abstraction or increase the ease of use? For instance, ease of use is increased by solving standard diagnostic tasks, like retrieving all available ECUs and identifying them automatically, something you always need to do in the beginning when you want to talk to a car. In this example, the SDA, we have the SDA function, get identified targets. It will find all available ECUs. It will identify each variant, and it will return results as a list. Abstraction is achieved by many ways. One way is by using our, as you can see on the left here, our application guidelines, also called AGL. It is possible to define just once in AGL how the SDA can find, as an example again, the available ident values in ODX for an ECU. This can be, for instance, a special semantic attached to the ODX service, or many different ways like naming conventions. Once this is done, if you've done this once, then you can reuse it. And for the calls, all other ECUs, and you use the same method, and you do not need to know any ODX data names. More complex tasks for a single ECU can, for instance, be solved by using ODX jobs or even OTX scripts. Tasks like determining the complete state of health of an entire vehicle and all of its ECUs is done by programming this once in C++ Java or OTX. This is then used by all data departments who do not need to take care of this implementation. Again, the other departments do not need to know how ODX or MCD work to be able to use this API. So, as we said in the beginning, these diagnostic functions should be developed just once in engineering and then reused. All following steps in the car's lifetime will reuse the features, providing ease of use not only for engineering, but also for all steps in production and after sales. The amount of tools our OEM uses is often underestimated. The time and money that can be saved through the entire process is usually much larger than expected. Also, normal programmers who are not MCD ODX experts can easily create their own scripting, their own automation. And as we said previously, the SDA is remote capable. It can be split into a server and client and will take over the remote communication. In this example, the SDA is running on the Winnie 2000, but it could also be a PC, a Raspberry, a telephone, or HPC like a Headune. All that is required is a secure TCP connection. To connect to a remote vehicle or ECU via the SDA, at first the connection information is needed. Remote devices connect to their software broker and inform it of their availability and their connection information. The SDA then can request this information and use it to connect to the remote system. The SDA works also in a high latency environment, meaning it can be used worldwide for access, as long as a secure remote connection can be established to the target. So, as an example here, using the SDA remotely is already integrated in Softing products. For instance, here, and some people might be familiar with this is our Softing DTS9 product. We have a section here, Smart Remote Verbindungen, which lists all the available remote devices that this DTS9 instance can connect to. Simply double-click on it and you are connected remotely. And from there on, you use DTS9 just as if you were connected locally to the device. There's no difference in the usage. So how do you do this? Connect remotely through such a long distance and are not that latency dependent? Well, let's compare it with MCD and SDA. If you use MCD and you want to identify an ECU, you have many calls for just one ECU. And if you want to identify 50 ECUs, you have hundreds, maybe even thousands of calls just to identify your vehicle. This causes high latency and is very dependent on the connection quality. Well, what the SDE does is the SDE tells you send a list of the ECUs you want to identify. The SDE does the identification on its own itself and returns the list of the fully identified ECUs, making all of this just a single call. Additionally, the SDA will complete this task even if a connection loss occurs. So if you send a flashing request down and the flash is ongoing and you have a connection loss, if you use the SDA, it will continue the flashing locally until it's done. If you did this via MCD, the flashing would abort and you would have a half-flashed ECU. So let's compare this again. Here you have an example. This is the SDA to read identified results, to read idents. If you want to do this synchronously, you have the entire program here on the top left part. It is the entire thing. It is starting the SDA, connecting to the, selecting the project, connecting to the device, identifying it, and getting the results. If you want to do it asynchronously, it's a bit larger, but still small. If you look at this in MCD, you need a lot of code to do this, and this is even complete. It's many pages more just for the synchronous result. So here you can see the ease of use. Let's take a look inside. So I'm just going to open here our Visual Studio, and we have here, for instance, a detailed program. You can see over here, and this is a complete program that has two ways of flashing a vehicle, synchronously and asynchronously, instantly an entire program if you do not use any GUI for this. Most importantly, here on top, using softing SDA. That's the important part. I'll just have a quick step through how do you actually use it. Well, you just get a smart API instance, you initialize it, you select a project, you select a vehicle information, you connect to your predetermined interfaces. You can also here dynamically connect to choose from a list if you want to the remote devices. And here in this case, we have already pre-configured it. Then this method we already showed earlier, get identified targets. It will return the entire list of what is inside of your vehicle already pre-identified. With this list, you can just simply go, well, what flash sessions are available in my project for this list of ECUs? We just compare these two together and you see, well, these are, it returns all the flash sessions available in your project for these ECUs. And then in a simple for loop, you can say, execute these flash sessions for me, and it will handle all of that. If you want to do it asynchronously, it's not much longer. Here, we make it a little bit different. We make a list of all the sessions that we want for the entire vehicle, and we execute this flash session list. We send it down, and here in this while loop, we just wait for it's done. We can use here, do other things here, show progress reports, or do whatever we want while it completes. Again, as I said, if we send this execute flash and we get a connection loss because the vehicle lost its Wi-Fi connection, no issues, it will just continue. Okay, let's go back. So the Smart Diagnostic API for us here at Softing, it's a success story. We introduced the Smart API for our own products. We started using it a lot with DTSI Monaco, and then later decided to fully change everything in Monaco entirely on the SDA and use it in other products. Then we had, for one very large OEM, some technical users who also wanted to give it a try. They tried it. They had to very quickly develop very small applications, and those spread very quickly amongst the different departments. And this way it became very known. And now the official remote administration tools and everything is already from the OEM is now based on the SDA, and he sells those tools based again on the SDA. It's not only the OEM, because the first tiers also noticed this, and they are also using this on approval. If the OEM approves it, they use the same API, and their products are already starting to be based on this as well. So we can see a very large and very natural spreading of the SDA here, simply because it is so convenient and so useful. So the SDA functions are based on a softing standard, but this can be easily adapted by yourself, or if you want, by us. It is used in many different application areas. For instance, in software over the air inside of a vehicle. It is used in test stands, in nightly build pipelines, in many, many, many more applications. So I hope I gave a good overview of how we use it and how we solve those requirements, and would hand back over to Julian.
Thank you, Andreas. So to give you a short overview, or to kind of summarize what you've been hearing the last minutes, I would like to point out again a very important part of using this diagnostic approach And this is the high scalability of the solution. You see on the left-hand part, it's the classic diagnostic approach with the MVCI, or the service-oriented approach with using the SDA as an point-to-point connection from the PC into an ECU via a wired connection with that interface on the left-hand side. On the right-hand side, you see here another approach, and this is the autark use case, meaning that all the diagnostic functionality and information is run autarkic on an interface you see here, and the connection to the PC is managed or connected via Wi-Fi. But on top of that, you could also realize additional use cases, and this is the most important part, that also the future use cases can be covered by this diagnostic and service-oriented approach. And this is when you have a cloud or internet connection in the back. You see in the middle the connection to the vehicle with an standard Wi-Fi interface. And the Softing SDE runs here on a test stand or test PC, which is steered by a cloud or by a production system, for instance. And last but not least, again, this is a use case for the autark diagnostic use case. And this is where the Softing SDE runs entirely on a vehicle, on an HPC, for example, realizing these use cases like vehicle health, so gathering information from the vehicle, combining and compressing it and sending just information back to the cloud for further analysis. Or what also could be realized is the remote use case. You see the PC on the right hand corner on the top. So you could also establish, of course, a one-to-one connection from a PC to a single vehicle and do direct diagnostic communication with that vehicle. So again, a huge variety of use cases from the development to the after sales, and through the entire life cycle, you could rely on just one single diagnostic system to cover all your use cases. Let's come to the summary of that. In the beginning, we've been talking about the classic diagnostic approach based on ODX and OTX. So the important information is that this is being reused also in this concept for service-oriented diagnostics. And very good about this is that it is a mature diagnostic system. It has been in use for many, many years and therefore tested, and the functionality is great. We've been talking about use cases, new EE architectures driven by functionality or mega trends like autonomous driving. This, of course, leads to new requirements and also has an enormous impact on diagnostics itself and diagnostic functionality. These use cases then are covered with the SDE and the functionality, what Andreas presented to you. So the shift from single service execution to service-oriented diagnostics. And in the end, of course, we have that advantages. It's easy to learn compared to MCD 3 API. You do not have these 1,500 functions and do not need to know everything, but you just can execute one single functionality, the vehicle health, for instance, to get all the information out of your vehicle. The high scalability was the slide you've been seeing before. So through the entire life cycle, you could reuse, implement, and test based on one single diagnostic stack. And of course, implement it once and use it multiple times. Again, this is a very good advantage. And what also is good about this when or in terms of implementing different applications, for example, engineering testers or after-sales testers, here again, the development of these applications becomes very, very easy. and gives you the possibility to speed up your development and in the end have a faster time to market. One additional note at that side, this webinar what we've been seeing today is the predecessor of a webinar we will hold on January 25. And this will be about the service-oriented vehicle diagnostics, the standardization, the current status, and how these use cases, I would say perfectly fit together to what you've been hearing today. Okay, thank you very much for your attention. As promised, we will now start the Q&A section. So I will have a quick look here in the chat. Again, if you have some questions, please feel free to just type it in the chat or in the F&A section. Okay, I see here. Maybe Andreas, a quick question to you. What would be the real benefit of using the SDA and this service-oriented approach? What do you think?
Well, it's pretty much the summary of what we showed just before. It's that you have just a few developers who need to know in-depth diagnostics, who know maybe a bit about MCD and about ODX data, and they just develop their diagnostic functions once. And this you can then test completely finished and make sure it's perfect in engineering part. And then all the other developers, many teams, if you want to develop a new application, you don't have 10 MCD experts. Right. Yeah, you hand out to someone to develop your application. They maybe have diagnostics knowledge or something, but they're not all MCD experts.
Okay.
And so that becomes very difficult often to maybe even outsource or do simple tasks. And with these diagnostic functions, you no longer need this. They are so simple to use. If you have just a simple programming background, you can very easily and very quickly complete your diagnostic tasks.
Oh, okay, interesting. So in the end, you will need less developers, you say, to develop your and use the functionality afterwards, right?
Yes.
Okay.
And also we have examples, for instance, for some OEMs where in the team they need something specific, and then they use a very large tool to do this, manually using the GUI or something like that. And they say, well, I only need to automate this one part, and how do I do it quickly? And they are not very well. They're just simple developers. One knows some Java scripting or some C++, and they can just use it, and they found out, hey, well, I can do this myself. And they just very quickly do their automation tasks they want to do.
I see.
And
Okay. So you're saying that this API is very simple to use. I was not able to follow everything what you've been saying, but is it right that you have the API in multiple programming languages available, so that dependent on what not profession, but what capabilities you have at an OEM or in first tier, you could use it in different languages?
Yes.
Okay.
Exactly. And not just languages, also environments. I mean, we have people who like Windows, we have people who like Linux. And we can develop in your C++, you can develop it in Java. We even have it for Python. So whatever fits to you, you can use. So yeah. So this really opens up the possibilities for many people to use it.
Yeah, perfect. Great. Okay, just quick look at the chat or an F&A.
Any questions about anything of this?
Okay, I don't see more questions here. So with that, I would just end this webinar. Thank you, Andreas, for showing us the details. And for you, the participants, you see here our contact data. So just in case you have any questions, technical questions, or also other topics you would like to know, you just could approach Andreas or me via email. Just send us a mail, and we will try to answer your question, or at least get the people together to find an answer to your topics. Yep. Yeah. All right. Oh, there's one question. Sorry, I just want to just didn't want to finalize. Just get me back here. Thank you. What are the proprietary tools used in this layer?
My tools. I'm not sure I understand the question fully. I mean, for this smart API layer, it's programmed in C++. So it is developed by us. To maybe go back to this answers the question. Let me just step back quickly.
Yeah.
If we're talking about how to use this layer, I think maybe this is the best part here. You see, the Smart Diagnostic API is developed by us in C++, and it offers many functions, as we already saw. We could go, for instance, like get identified targets. But all the SDA functions can be replaced by your own implementation, meaning if you need that function, you can implement yourself. This how does it find the identity ECUs? Does it use a functional diagnostic services, or since to each ECU service? This you can, if you don't like the approach the SDA uses, you can implement it yourself. And so using, again, standardized things like OTX, Java jobs, or write in C++. Proprietary tools other than this we have not used. I mean, of course, there's some open source in there, but that is all clarified and revealed, which open sources are included. There's a list. If you install the setup, you get to see exactly what we used.
Okay, thank you. So let's quickly check again the chat and the Q&A section. Yeah, don't see any more questions to that. So again, thank you very much for your participation and your attention. And with that, I propose to just end this webinar. And again, if you have some questions, just let's stay in contact with Andreas or me.
Thank you very much. And everybody, have a nice day.
Thank you. Bye-bye.
Bye-bye.